So good afternoon, guys. So in the last class, we have discussed one more application of magnetic force, and that was your own Hall effect. And incidentally, we had actually planned it in such a way that you will have your experiment on Hall effect also happening in the same week. So that way, we thought it will be a reinforcement, and you would have learned it twice in the same week. I don't know, that was our attempt. I don't know how much you people understood it or received it. Okay, now that there were totally, I think, 5 or 6 applications that were there for magnetic forces. The first was velocity selector. And after velocity selector, we had E by M. And then we had cyclotron, mass spectrometer, Hall effect. Okay, so these were the 5 applications of magnetic forces. Now, once we were done with all that, we started saying that, all those discussions were confined to movement of charges, individual charges in a magnetic field, and the force exerted by the magnetic field on those individual charges. But now we are going to look at something else. We are going to look at a collection of such moving charges. A collection of such moving charges would be current. Okay, so then what would be the force is what we are supposed to be seeing today. Okay, so for that, what we'll do is let us consider a conductor. And initially, it is in a magnetic field, a uniform magnetic field B. There is no current. You find that this wire is not going to get deflected. But then look at the next picture. You have a current in this direction, and you're seeing that the part of the wire which is in the magnetic field is experiencing a force FB in this direction, because of which the wire itself, the force on the moving charges gets transmitted to the wire, and the wire itself experiences a deflection. Now, in the next picture, you're seeing that when you reverse the current direction, what happens? When you reverse the current direction, you're finding that FB is also getting reversed. So now the next attempt, I did all that in the last class. The next attempt is to find the expression for this magnetic force. Okay, so now what we will now do is we will consider a straight conductor, a straight current carrying conductor. Let's assume that the current is uniform, and we are going to just take a length L of this conductor, a length L of this conductor, and it is lying in the uniform magnetic field. There is a current as indicated by this arrow. Okay, now, first of all, you have to know how much charge is there within this length L. How much charge is there within this length L? We have to see. Okay, so before that, we know it's a conductor, and in a conductor, we know it is the electrons which are going to carry current, and you know that the electrons would be moving with an average velocity Vd. The electrons will move with an average velocity Vd opposite to the current direction. Right? So let us look at what is the force on one such electron. It will be Fb is equal to minus E, where minus E is Q. Okay? Charge of the electron minus E Vd cross B. So you can just use your right hand rule. Okay? Vd cross B. Vd cross B, if you do, you're going to see that there is going to be a force. Okay? Okay. You're going to see that there is going to be a force on this electron, okay, and that force is given by minus E into Vd cross B. Vd cross B, so the force is going to be to the right. Okay, now let us look at all the electrons, all the moving electrons lying within this length L. Let us consider all the moving electrons lying within this length L. Okay, so let the number of electrons within this length be N. Let N be the total, capital N be the total number of electrons lying within this volume or within this length of the wire. Okay, so then the net force on the wire is going to be capital N into the force due to a single electron. Capital N into the force due to a single electron. Now we have to attempt to get what is this capital N. Okay, so for that, what we will do is, let us consider the volume of the wire. Okay, let us say the area of cross section is A. Let A be the area of cross section. L is the length that you are interested in. Therefore, the area of the cross section into L is going to be the volume of the wire in the magnetic field. Okay. Now, you know that 1 meter cube of the wire, 1 meter cube of the wire has small n number of free electrons. What is small n? It has got another name. Anyone? Small n has got another name. What is it called? It is called the, anyone? Yesterday also we have seen in the lab, live yesterday. What is small n called?
Charge density.
Charge density. It's a number density, number of charge carriers per meter cube. So I know that in 1 meter cube, I have small n number of electrons. So in a volume AL, how much will be the charge? What will be the number of charge? So N will be equal to, anyone? N will be equal to small n into LA. Capital N will be small n into LA. Cost of 1 mango, cost of 10 mangoes. That's the logic. Okay. So now what we'll do is, instead of capital N, we will put small n into LA. And now you see here, you're seeing some familiar expressions. You're seeing small n, then you're seeing VD, and then you're seeing charge. Small n, VD, and charge. So let's put them all together. So what is this going to be? You've seen that for a current density in a conductor is given by minus NEVD. Can someone explain why this minus came for a conductor? J is equal to minus NEVD. One student in the class had sent me a message on this. Why this minus? Anyone? It is not, the current direction is opposite to the direction of the flow of the electrons. That is convention. So that minus. VD vector is anti-parallel to J vector. J vector on the other hand is I by A. Current by A. Okay, so instead of minus NEVD, we will write J. So J into LA cross B. J into LA cross B. Okay, now let us see what we can further do. You know that current is equal to current density equal to current divided by area. So from this you can say that current is equal to current density into area. So we will simply take out this and club them together and call it as current. So you get current, but then there is a cross product here. There is a cross product, which means you have to have two vectors. Now what you will do is, current is a scalar, so you cannot put a cross product there. So now the length itself, you're going to make it as an area vector. You're going to convert the length of the wire in the magnetic field as the area. You're going to make it a vector quantity. So L becomes a vector quantity. Till here you see, L was not a vector. Your J was a vector. But now J is going to relinquish its directional property to L. And simply it's going to get multiplied by A and become current. Current I is J into A, which is a scalar quantity. So the direction is now shifted to L. Okay. So L obviously will have the direction of current. Because after all, J has given its directional property to L. Therefore, L is going to have the direction of current or current density. Therefore, you get the final expression for FB as IL cross B, where L is the direction of the current or current density and B is the direction of the magnetic field. Okay, now what is the advantage of this equation over FB is equal to QV cross B? How is this equation a better equation than that? Anyone? We could have just retained it in that old form only and then put the total number of electrons into, the number of charges. You know the number of charges is capital N. So capital N into Q VD cross B. We could have left it like that. Why did we have to write it as IL cross B? Anyone? Are you following my question? Direction of current, yes. Direction of the current, yes. You have partially answered that. I may be talking about an N-type semiconductor where electron is the major carrier, where the charge is moving opposite to the current direction. Or I may be talking about a metal where the electrons are the carriers. They are moving in a direction opposite to the current direction. Or I may be talking about a P-type semiconductor where holes are the carriers. Holes are moving parallel to the current direction. Okay, so if I have to talk in terms of the charges, then I have to bother about what is the direction of VD. Then what is the material? All these things I have to know. And another thing, please remember, drift velocity is not something that you can take a device in your lab and then put it across the sample and measure VD. Drift velocity is not something that you can measure directly. Similarly, the number of charge carriers you cannot measure directly. Whereas look at this form of the equation, you see, I. Current can be measured. All you need is an ammeter. You have an ammeter, you can measure current. L, you can always measure. You just have to take a scale and measure L. Magnetic field, after all, you are applying. You know what is a magnetic field you have applied. You can use a Gauss meter, find out what is the magnetic field that you have applied. So this is the more practical equation. FB is equal to IL cross B is the more practical equation. All these are measurable quantities. And next thing is you don't have to bother about what is the carrier. You just have to know the current direction only. Okay, so that's the reason why this is actually a macro equation as compared to QV cross B. QV cross B, on the other hand, is a micro equation. It's an equation whose properties you can use, and the use of those things maybe you can see in a cyclotron and all that. But then you can't really take one electron, find out what is the force on it. So that is actually academic. What you have done there is an academic exercise, whereas FB is equal to IL cross B is a practical equation. Okay, now I set one condition. I don't know how many of you noticed. I said the wire is a straight wire. And I said the magnetic field is a uniform magnetic field. Okay, now let's relax those conditions. Or before relaxing those conditions, let me just... Is Kiranmai not coming to the class? Oh, she's here. What happened, Kiranmai? Maun Brat or something?
Ma'am, yesterday I was not in the class.
You were not in the class. I noticed that. You were missed. You are one person who
Yeah.
takes pity on the teacher and takes care to unmute and answer. I know there are some others also who know answers, but then they are so lazy to unmute. You were missed. Okay, so now we have seen that in the vector form, FB is equal to IL cross B, which when you write for magnitude, it will be FB is equal to ILB sine phi. Sine phi. And what is phi? Phi is the angle between L and B. And clearly you can see that FB will be perpendicular to L and B. It will be perpendicular to both the L vector and the magnetic field. Or it will be perpendicular to the current direction and the magnetic field direction. Okay, now let us just play with phi. Let's play with phi. What happens if phi is 0 or 180? Phi is 0 or 180 means L is parallel to B. The current is parallel to the B vector magnetic field or anti-parallel to magnetic field. Then what happens? You know, sine of 0 or sine of 180 is 0. Therefore, the force is going to be 0. So from this, there is an application. If you don't want your current carrying conductor to be affected by external magnetic field, put it parallel or anti-parallel to the magnetic field. Okay. Then next thing, when can you see the maximum force on a current carrying conductor? You can get a maximum force on a current carrying conductor when you put your current perpendicular to the magnetic field. When the current is perpendicular to the magnetic field, then you see that angle is 90, sine of 90 is 1, or the force is a maximum, it is ILB. Then somebody will ask, well, there is one student in this class who keeps asking these kind of messages he keeps asking. What if phi is, ma'am, you didn't discuss the entire thing, ma'am. What if phi is 270? What if phi is 270? Anyone? Think about it and do it. Okay, next. Now let us relax the conditions one after the other. What if my wire is not a straight wire? The wire is not a straight wire. Let us say I have a twisted wire. Let's say I have a twisted wire like this. And it is lying in a uniform magnetic field. And it is carrying a current. Then what I need to do here is I know the straight wire, but I don't know the formula for a twisted wire. So from that straight wire, I have to get this formula. So what do? I consider this to be made up of a number of straight elements. I consider this to be made up of a number of straight elements, each of length ds. Each of length ds. So take it as a ds vector in a magnetic field B and find out what is the force on that small length element ds. Obviously, the force is going to be a small force dfb given by I ds cross b. Okay. Now I want what is the force for this entire length of the wire. What we have been doing usually. Go for the method of calculus and just do an integration. And when you're doing an integration, you get the net force. And you know that this I is going to be common. It's a constant. Take it out. And the integral is going to have just ds cross b. The integral is going to have just ds cross b. Okay. Now we will relax one more condition. First condition that I relaxed was the wire is not a straight current carrying conductor, but the magnetic field is uniform. Okay, now I'm going to relax the second condition. What is the second condition? The magnetic field need not be uniform. If the magnetic field is not uniform, what does that mean? What is the meaning of saying magnetic field is not uniform? Magnetic field is not uniform means at different points, magnetic field may have different values. At different point, magnetic field may have different values. That is, B is a function of X, Y, Z. Okay, then what happens is you cannot pull it out of this integral. You can't take B out of this integral. ds vector can be written as some dxi cap plus dyj cap plus dz cap. I'm writing the most general case. And then you can do a cross product and then find the integration. But that's the toughest thing I have discussed. Most often you don't have to do all that. Okay, the magnetic field will be uniform. So if the magnetic field is uniform, then what happens? This cross B can come out of the integration. This cross B can come out of the integration. Therefore, what happens will be FB will be equal to I integral ds cross B. I into integral ds cross B. And this you do when B is uniform. B is uniform for the entire length of the wire. Okay, now look at this. What will be integral ds? I start my integration here and end my integration here. This is my wire in a uniform magnetic field. So when I do an integration from here to here, what I am going to get is going to be some I L prime cross B. I L prime cross B. And what is L prime? L prime is a vector. Listen carefully. L prime is a vector that you get by connecting the starting point to the ending point. It's a vector that you get by connecting the starting point to the ending point. And the direction is going to be as indicated here, and the length is going to be L prime. Are you getting this point, guys? If you do an integration of ds, if I take a small element like this and do an integration, what I effectively will get is going to be a straight line whose magnitude is this length, starting to the ending length. Okay, and the direction is as given here. So let's call it as a different vector L prime. So it is I L prime cross B. Okay, now to give you a feel for this, I've just tried to do a problem here. Look at this. What is the net force on a current wire with ends at 200 and 411? So the endpoints are 200 and 411 and carrying a current 2 ampere. And let's say, or maybe I can even say it starts at 200 and ends at 411 and carrying a current 2 ampere placed in a uniform magnetic field along the I cap direction. The magnetic field is along the I cap direction. So how will you do this? You have to use the equation if B is equal to I L prime cross B. Okay. Now, how do I get, if I know the starting point and the ending point, how do I get L prime? How do I get L prime? L prime vector will be equal to, this is your coordinate geometry. So it's going to be 4 minus 2. What is 4 minus 2? 4 minus 2 is 2 I cap. Then 1 minus 0 is going to be plus j cap. Then 1 minus 0 is going to be plus k cap. How many of you understood this? Anyone who has not understood this? Coordinate geometry, guys. If I have x1, y1, z1, and coordinate of another point is x2, y2, z2, what is the length of this? X2 minus x1, y2 minus y1, z2 minus z1. I've just used that. Okay. Now I know my L prime. So use it. Current is 2. So 2 into L prime cross 2I. Can't you do this cross product? I cross I, 0. J cross I, minus K. K cross I. K cross I. G. That's it. Okay. So when problems of this kind are given, this is the way you have to approach it. Now I'm going to ask you a question. What happens if you take a wire and put it in a magnetic field, uniform magnetic field, and the wire is going to start like this and end like this? And there is a current. So what kind of a current am I talking about? I'm talking about a loop. I'm talking about a loop of current, a closed loop of current. So current, what would be the force on this? Magnetic force on this?
0.
0. Because the starting point and the ending point can be anywhere inside that loop. It's the same. Okay, so you can simply say that it is 0. This is just from here that you have this famous result that, anyone can say that result? You have a very famous result which says that a current loop placed in a uniform magnetic field experiences a net force. How much? What happened? A current in a uniform a current loop placed in a uniform magnetic field experiences a force. How much? 0. Experiences 0 force. I'll write the answer because there will be some people who don't even want to think. So the net force on a current loop placed in a uniform magnetic field is 0. Okay. Okay, now let's just work out a numerical. Let's work out a numerical. So this numerical is going to be about suspending a current carrying wire in air. Suspending a current carrying wire in air by applying an upward magnetic force. By applying a magnetic force such that it will be equal and opposite to mg. Mg is the weight. So if you are able to apply a magnetic force in the upward direction equal to mg, then you can actually suspend this wire in air. So that's the philosophy of the problem. So let's read the statement. A straight horizontal segment of copper wire carries a current I equal to 28 ampere. What are the magnitude and direction of the magnetic field that you need to apply? That you need to apply to balance it. And what are the parameters that are given? I is given. Then length, is it there? No, length is not there. Okay, but then linear mass density is given. Linear mass density. So what's linear mass density? Linear mass density is mass per unit length. Kilogram per meter, you have to make it. Mass per unit length. 46.6 gram per meter. So convert it into kilogram per meter. So that's your linear mass density. Okay. Now let's assume that you're going to take a length L of the wire, some unknown length L of the wire. You're passing a current as this direction as shown here. You have to put it in a uniform magnetic field such that the magnetic force is in the upward direction and equal and opposite to mg. So first of all, what should be the direction of that magnetic field? You have to know how to use the right hand rule. So I cross B. B is into the plane of the board. I is like this. I cross B. So my FB is in the upward direction. So that's the reason why the magnetic field is shown as crosses into the plane. Into the plane. So I got my direction. Next, we have to find out how much is the magnetic field that you have to apply. So before we do all that, let us write the expression for the magnetic force. It is IL cross B. You can see that L and B are perpendicular to each other. L is perpendicular to B. Okay. Therefore, you can see that FB is going to be simply ILB. Sin 90 is 1, so ILB. And what is the downward force? Downward force is mg. So we can simply say that the magnitude of these two forces should be equal. Or we can say that B is equal to mg by IL. B is equal to mg by IL. Now you see here, we are going to slightly club together some terms. What are we going to do? Let's write G by I separately and then put M by L in a bracket. What is M by L? What is M by L?
Linear mass density.
Linear mass density. We have already got it here. Okay, so just substitute. G is 9.81. Current is 28 amperes. Then put your linear mass density and you get your magnetic field. So you need to apply a uniform magnetic field of 16 millitesla into the plane of the paper or the screen for you to have an upward force. Or one thing that you must have realized, the minute you started magnetism is the right hand rule. You have to be comfortable with the right hand rule. Okay, you can have questions where we are giving you an electron is entering a magnetic field. Okay, will it go like this or will it go like this or will it go straight line? Okay, instead of an electron, I'm going to give an alpha particle. In which direction will it go? If I give you a proton, how will it go? Or I give you some paths and then ask you, one is a deuteron, one is an alpha particle and one is a positron. So which is what? So for all this, you basically need to know charge and a comparison of masses. That is the first part of the chapter. Similarly here, the minute we come to current also, you need to know how to use your right hand rule. Similarly in the velocity selector also, you need to use the concept of the right hand rule. So the right hand rule is going to be very, very important all through magnetism. In Hall effect also, we are looking at right hand rule. Now let's try another problem. Actually, the author has done this problem slightly differently, but then you don't need to do all that, which is what we are going to discuss now. There is a wire segment. There is a wire segment placed in a uniform magnetic field B, and the magnetic field is pointing out of the plane of the page. It is pointing out of the screen. Okay. If the segment carries a current I is the current in the segment. So obviously the entire segment is going to have the current I only. What resultant magnetic force will act on this wire? What magnetic force will act on the wire? The only thing that is given is there are three sections of the wire. One which is a straight portion, then two which is a semicircular portion, and three which is a straight wire again. Okay, and R is given as the radius of the semicircle, and you have to find out what is the net force. In the book, the author has divided this semicircle into small bits and done integration and all that is not at all required. If you know the coordinate of this, and if you know the coordinate of this point, then I can get my L prime straight away, right? So which is what we will do here. So let's say that the net magnetic force is F1 plus F2 plus F3. F1 is on the first bit, F2 is on the second, which is a semicircle, and F3 is again on the straight line linear portion. For the first and the third bit, straight away you can see that the current is perpendicular to the magnetic field. Okay, so you can see that the force is ILB, ILB, ILB. No problem there. And what is the direction? So the direction I can see is in the downward direction. It's a downward direction. Okay, L cross B. It's the downward direction. Okay, now come to the semicircle. For the semicircle, no big deal. I know that R is the radius. So what will be L prime? L prime will be equal to 2R. L prime will be equal to 2R, and the direction is of current, you have to take it as from point A to point B. Same as in L. Therefore, the direction is also going to be the same only. So I will get F2 also in the same direction. F1 and F3 are downward. F2 also will be downward, and it will be I L cross B. So it will be I, L prime is 2R B, or I get IB 2R. So now add up everything. They are all parallel vectors, not a problem at all. Just add them. So 2IB L plus R. Okay, so the net force is in the downward direction. Okay. Fine. Now, so now we all know that if you have a region of uniform magnetic field and if you have a closed loop, this entire closed loop is in a magnetic field, then you know that the net force is 0. Okay, so let us think of a practical situation where we are going to see this. You have the poles of the electromagnet. So let's call them N and S, denoting north and south pole. So between them, there is a uniform magnetic field indicated by the red straight parallel arrows. And what we are going to do here is we are going to have a suspension system, okay, a suspension system and a rectangular loop. We're going to have a rectangular loop suspended between the two in such a way that this suspension can rotate. The suspension can rotate. Okay. Now let us take this loop and see. There are 4 sides in this rectangular loop. What will be the force on each of these sides? We can see. The force on this will be 0. Why? Why is the force on the side that I have marked? Why will it be 0? Anyone? What is the direction of current? Current is parallel to the magnetic field. Therefore, the force is 0. Similarly, I can show that the force here is also going to be 0. And you will find that here and here, for this arm and for this arm, there will be force. Force given by ILB. ILB. I is opposite in both of them. So you can see that the net force is going to be equal to 0. It is going to be equal to ILB minus ILB if L is the length. If L is the length. One force is, please remember the force will be perpendicular to B and L. That means it will be perpendicular to the page. It will be perpendicular to the page. One vector going out and one vector going in. So the net force is going to be 0. But then please remember the line of action of both these forces is not the same. These two forces forces form a couple. These two forces form a couple. So actually what happens is one force acts like this, one force acts in the opposite direction, so it will turn, it will turn. There is a torque on this loop. There is a torque on the loop. Okay, so you can conclude that when you have a uniform, when you have a current loop in a uniform magnetic field, then the net force on it is zero, but then there will be a torque acting on the loop. And what is this torque going to do? This torque, so whatever I have said is what I've written here. This torque, how much is this torque? Let us see. This torque can be shown to be 2IAB B by 2. 2IAB B by 2. You can show where B by 2. So I'm saying that this side is B, this side is A, this side is B. Okay, then it will, the force will act as if, the torque will act as if this is the axis of rotation, as if this is the axis of rotation. And you can see that it will turn the frame. It will turn the frame about this axis. The direction I showed is opposite. It will turn this frame of the current. Okay, and why will it rotate this loop? It will rotate the loop. Okay, it will rotate the loop so that the plane of the loop becomes parallel to the magnetic field. It will turn so that the plane of the loop becomes parallel to the magnetic field. So if I have my north and south like this, then the plane of the loop should become like this. The face of the loop should look at the current loop, should look at the north pole. Then there will be no torque. So it just attempts to turn it. Okay. And in electrostatics also, we have studied such a situation where an electric dipole is rotated so that it becomes parallel to the electric field. Similarly here, the loop of current is rotated so that the plane of the loop becomes parallel to the plane of the loop becomes perpendicular to, not parallel, the plane of the loop becomes perpendicular to the magnetic field. Okay, now all these things that are written in English can be written in the form of an equation. Can be written in the form of an equation. You can write it as torque equal to, you can write, and let us say that there are n number of turns of the loop. Sometimes you can have a coil through which current is passing. If n is the number of turns of the loop, then the net torque acting is going to be NIA cross B. NIA cross B. What is the I? I is the current, N is the number of turns, A is the area vector. A is the area vector. What does that mean? I'll show you. Let us say this is A and this is B. Then area is going to be equal to AB. Okay? And let's say the current is flowing like this. Then what you need to do is use your, or let me put it in the opposite direction. What we'll do here is, let's just put a loop here. And let me just show the current direction as this. Okay, then what you need to do is put your right hand fingers in the direction of the current in the loop. Put your right hand fingers in the direction of the current in the loop and look at the direction of the thumb. And look at the direction of the thumb. So the thumb gives you the direction of the area vector. The thumb gives you the direction of the area vector. And magnitude of the area vector is simply small ab. You can apply this for a circular loop, for any shape of the loop. Okay, the magnitude of the area vector will be the actual area, and your direction is going to be given by the right hand rule, where you put your right hand fingers in the direction of the current. Okay, in Gauss law, electrostatics, we had an area vector, but there an outward normal we have taken. Here also it's a normal. The direction of the area vector is a normal to the surface, but which normal? There is no inward and outward. The direction of the normal is given by the right hand rule. So once more, there is a right hand rule. Okay, so now what you need to do is we have A cross B, A cross B. So now you have to look at what is the angle between vector A and vector B. Okay, now what we'll do is let us say that we have a uniform magnetic field here. Let's say there is a uniform magnetic field. This is my magnetic field. So at this point also the magnetic field is going to be like this. This is my magnetic field vector. This is my A vector. So now I have to look at this angle. This is my theta. This is the angle between A and B vector. So this is the way you get the angle between the A and the B vector. Okay. Now, so what is the torque trying to do? The torque is trying to turn this so that theta becomes 0. It's going to turn it so that theta becomes 0. So because of the torque, let's see how the final picture will look. So this is my B vector. Then finally, my loop would have turned and become like this. Okay, this would be my loop now. And if I look at my area vector, I will find that my area vector and my B vector are parallel to each other, or theta becomes 0. Theta becomes 0. So this is what the magnetic field is going to do to your loop. The force that is there on the two arms will become coupled, and it's going to act on that loop and turn it so that the plane of the loop becomes perpendicular to the magnetic field, or the area vector becomes parallel to the magnetic field. These are two things I'm telling you. The plane of the loop becomes perpendicular to the magnetic field, or the area vector becomes parallel to the magnetic field. So whenever a problem of this kind is given, when theta is defined, see what is theta. Are we talking about the angle between area vector and magnetic field, or is it between the plane and the magnetic field? If it is between the plane and the magnetic field, convert it into the area vector and the magnetic field. It will be 90 minus that angle. You'll get it. Okay. Where do you have a use for this torque? I'll give you an example where this torque is going to be useful. In fact, even in your generator, it is useful. Not in your generator, what happens? You're going to turn it. It's going to keep rotating. Okay, I think it's too premature for me to talk about that. That I'll talk in the next chapter. But before that, let us see where this torque is going to be useful. In the case of analog voltmeters and ammeters, what is analog? You know what is digital? Digital is when you see that 7-segment display and you are able to read 25 volts. Unfortunately, you didn't enter the lab. Okay, so when you're able to see that, that is a digital meter. But then if there is a needle that is going to move, like for example, your speedometer in your car, the speedometer in your car, that is actually a analog meter. It's actually the needle which is moving on a scale. Okay, similarly, voltmeters and ammeters also, you can have analog meters. So what happens in an analog meter, we'll see. Here is a scale. The pointer is going to move. So how does it actually work? So you can read here. The reading is displayed by the deflection of a pointer over a scale. And it works by measuring the torque exerted by a magnetic field on a current loop. Let's say you're interested in measuring a current. So there is a current loop through which there is a current passing. And you can see that torque is directly proportional to current. Larger the torque means larger is going to be the deflection. So there is a coil mounted so that it can rotate about its axis in a uniform radial magnetic field. So this is your magnet. So, and also there will be a spring which is going to give it a counter torque so that, it's able to, otherwise, no, nothing stops it from going. Instead of going through 2 millimeters, it may just go like this. To stop it, there is also a spring mounted to give it a counter torque. So an analog voltmeter, or for that matter, any analog meter, works on this principle of torque on a current loop. Okay? And larger the torque, larger is the deflection. This is actually not really part of the syllabus. I just thought I should just mention it. So that's the reason why I'm mentioning it here. Those of you who are interested can just go through it. Not something that one might ask in an examination and all that. Okay, so with this, we are winding up the chapter. Anything you want to ask? We have 5 minutes left. I hope you know that Tuesday is your exam. I'm sorry. Uh, Tomorrow is your, what is it tomorrow? Anyone?
Quiz.
Yeah, tomorrow is your quiz. So please get prepared for tomorrow's quiz. What is the syllabus?
30 and 32, ma'am.
30 and 32. Yeah, what is 30? Which chapter is that?
Capacitors, ma'am.
Capacitor. Capacitor, and now this is magnetic force. Okay, so if you prepare for these two, already 2 chapters you wrote a quiz two. Now this, if you write, no, it is like if you are really preparing for the quiz, that's actually a preparation for the test two. Okay, so that's the way we have planned it. And another thing, guys, our labs are over. I hope you know that. 8 experiments are over. Maybe in the next few days, we'll put up the marks on the LMS. All the 8, I have already corrected the correction for 7. See, in your section 1, Madam and I, we are taking turns and correcting. Okay, some experiments she has corrected, some I have corrected, but don't worry about whether somebody is lenient and all that. No, whoever corrects one set first, will pass the marks to the other faculty so that the faculty gets to see the way the grading is done. So the other section is also marked in the same way. We have kept an upper, a lower, and what is the average, and accordingly only corrected. I'm sure all of you will agree with me that 18 is not the mark that most of you deserve out of 25, but most of the time we try to give you 18. In some cases, we have gone to 17 or 16. That is when somebody submits, 5 days and 6 days after the last day. And some students haven't even bothered to submit. So such people are going to be given one more chance in the next week. If you don't make use of it, and similarly, there are some students who had who were down with the COVID, or parent was down with the COVID and could not submit. Such people can also make use of this opportunity. Okay, they'll just be looking at the LMS, and even on the WhatsApp group, we'll put a message. But please don't create a situation where we are forced to give you an NC and you have to repeat the subject. Please don't do that. Okay, somehow finish this subject. Okay, with that, I'm winding up. Anything you want to ask? Yeah, anyway, you will not ask. Okay, good day then. Can leave.
Thank you, ma'am.
Yeah.